Hello, this is part 2 to chapter 12 in your textbook. In this chapter, we've been talking about testing relationships, and in this lecture, we'll talk about the concluding portion of the chapter, which focuses on a number of different components concerning testing relationships. So let's recap briefly. Last lecture, we talked about the normal distribution, z-scores, and t-scores. And we pointed out the importance of using normal distribution to determine where exactly we stand as far as z-critical values and t-critical values so that we can understand the significance for the variables we're interested in studying. So we know that we use z-scores when we're dealing with larger samples. In the instances where we don't have larger samples, we use t-scores. Within this section of the lecture, we're going to talk about hypothesis testing, as well as some errors that you can make while hypothesis testing, interpreting those values that you get from the test that you use, and the different types of tests that you could use. So let's refresh for a minute and think about the different forms of hypotheses. It's something we've talked about earlier in the semester, but just to make sure we're on the same page. So when it comes to a statistical hypothesis, this is a hypothesis that states the value of the population parameters and talks about the relationship between two or more variables. So a statistical hypothesis is going to be something that you can actually test using a statistical test. There are two types of statistical hypotheses that you can have, and that's the null hypothesis or the alternative or research hypothesis. Your text uses the phrase research hypothesis a lot, but I'm more comfortable with using the phrase alternative hypothesis because that's just the way that I was trained as far as statistics is concerned. But they both mean the same thing. So the null hypothesis is something that we talked about before, and that's the hypothesis that states that there is no relationship between two variables or no difference in what we see in our sample as it relates to the population. So there's no difference between what we observe in our sample and the population. There's no difference between those two variables. There's no difference between two or more groups. There is no difference that exists there. The alternative hypothesis or the research hypothesis states that there is a difference, that there is a relationship between these things. And this is what we expect to see if a relationship exists for our variables of interest. So let's think about it with our example we've used throughout the semester, education and income. A null hypothesis would say there is no relationship between education and income. An alternative hypothesis would say that there is a relationship between education and income. If we wanted to make a directional alternative hypothesis, we would say that as income increases, as education increases, income increases, or as education decreases, income decreases, or as education increases, then income decreases. Those are all examples of directional hypotheses. Now, the direction could be a positive or a negative direction. It could be an inverse relationship as well. That's not a major concern, but alternative hypothesis can come in a couple of different categories. But the null hypothesis always states that there is no relationship between the variables of interest or no difference in what we see here as opposed to what we see in the sample population. Now, when it comes to testing hypotheses, we test the hypotheses and we draw conclusions about whether or not the null hypothesis is accurate or if the null hypothesis is inaccurate. When we test using statistical tests, we start from the place of the null hypothesis. So we start with the assertion, to be as objective as possible, that there is no relationship between the things that we're interested in. But when we go through and to complete the test, we have to make a decision as to whether or not this is actually true. There are two major errors that we can make in the process of making this determination. You can make a type 1 error or you can make a type 2 error. So a type 1 error, when you make your decision after you conducted your test, means that you reject the null hypothesis when it's actually true. A type 2 error, that's one that is slightly less likely or something that's less observed for obvious reasons, because we wouldn't really know if we made that type of error. When the research fails to neglect the null hypothesis, even though it's false. So to put this in layman's term, when you make a type 1 error, that means that you start out with the null hypothesis, you run your test, and then you conclude that the null hypothesis was wrong, and you say, no, we have to go with the alternative. There is a relationship, but a relationship really doesn't exist there. If you decide that a relationship exists there and there wasn't one there, and you reject the null hypothesis, then you committed a type 1 error. But a type 2 error would be the opposite of that. So a type 2 error would be when you're in the process and you have the null hypothesis, you look at your data, and then from your data you say, okay, this is actually true. There is no relationship between these two variables. And then you end up making the error of keeping the null hypothesis when in all actuality you should have rejected the null hypothesis. That's the terminology we use when it comes to hypothesis testing. We either accept or reject the null hypothesis. We always talk in reference to the null hypothesis. So if you commit a type 1 error, that means that you started out with the right one, but you chose to reject it. If you commit a type 2 error, that means that you rejected it when you should have kept it. So my way of remembering this is that the type 1 error always happens when you started out with the right one, but you rejected it. And we determine all of this using statistical tests, using tests of statistical significance. If we make these errors, it comes from our assertions that we make from our statistical tests, because those tests the probability of making a type 1 error. This is why this is the one that we know the most about, because the statistical test and how we set up our confidence intervals is all centered around type 1 errors and how confident we want to be in our results in what we find. So if you remember in last lecture, I talked about Maury Povich and the Morris Show and how we are 99% certain that that person is the father of the child. And I used it as an example. And I said that within our research, that's not something that we can do explicitly. Well, using that same type of thinking, that's how we determine whether or not we made a type 1 error. We usually set it at a 95% confidence level, right? So we decide that we want to be 95% sure. That means that there's a 5% chance that we're not right. That 5% chance is our chance of making a type 1 error, which means coming to a conclusion that the null hypothesis is not true when it actually is. There's a 5% chance that we did that. We don't necessarily test for our ability to accept the null when there isn't a relationship between them, the type 2 error. We test for and we use our confidence intervals reflect the levels of confidence against a type 1 error. So our decision to accept or reject the null hypothesis is all grounded in those statistical tests we talked about. So it's all grounded in our comparison of our observed statistic, test statistic, and the critical value, which I'll talk about on the next slide. But as I stated earlier, we have our common levels of statistical significance that we operate from. It's the 0.05 level, which would be 95% confident. We have the 0.10 level, which will be 90% confident, the 0.01 level, which would be 99.9% confident, and the 0.0001 level, which would be 99.999% confident, which is what they use for DNA testing. And all of these flipped on their sides means when it comes to making a type 1 error, we give ourselves a 5% chance of making a type 1 error, a 10% chance of making a type 1 error, a 1% chance of making a type 1 error, and a 0.01% chance of making a type 1 error. So before we move forward, I want to make sure that we get a firm foundation in understanding how test statistics and critical values work. These are what we use in order to determine if there is a relationship between a few things. So you have your observed value and you have your critical value. This is something that you get as your output when you run a statistical test on a computer, or something that you get when you calculate by hand using the formulas for the different tests. So first, you have your observed value. This is the value that is calculated by you, the researcher, whether you're using software or you're using pen and paper. That's the value that you come up with. So you have a observed Z value or an observed T value. Remember we talked about that last lecture. So you end up with this value that you have. That is going to depend upon your data, something that is calculated by you. But then you have the critical value. The critical value is the value that is standardized, and it's the one that can be found in your appendix of your book, Appendix A and B, if I'm not mistaken. But that is the value that you need to hit in order to have statistical significance at your level of confidence that you set for your study. So this means that you have a value that's already outlined and standardized in a statistical table that tells you if when you compute your numbers for your data, it is this value or higher, then there is a statistically significant relationship between the variables you're interested in. So it's the number that you have to hit. You have to hit this number or higher in order for there to be a statistically significant difference between those two values or the variable you calculated and the population there. So how do we go about testing a hypothesis? Well, the first thing that you have to do, and something that we've already practiced within this class, is to state your null hypothesis and your alternative hypothesis. It's very important for you to start out there, because the only way you can determine whether or not your assertions are true is by stating your null hypothesis and your alternative hypothesis in the very beginning. This is where you draw your conclusions from the literature, and then you draw your conclusions there. You come up with what you predict as your educated guess to be the relationship between the two variables, and then we move forward with testing. So making the decision is the portion where you come up with what you believe is the relationship between the two. You make your decision and you're going to choose to test the null hypothesis. After you do that, you decide whether or not you want to do a one-tail test or you want to do a two-tail test. A two-tail test is the standard, because if you're choosing a two-tail test, that means that you are not making some sort of assertion about what the relationship looks like between the variables. You're just saying that there is a relationship between the variables. The one-tail test focuses more on the direction of the relationship between the variables. So let me give you an example. A two-tail test will be if you're testing to see if there's a relationship between education and income. A one-tail test would be if you're testing to see as education goes up, does income come down? Because you're focusing on that relationship there. And if you use a one-tail test instead of a two-tail test, the only way that you can reject the null hypothesis is if that relationship looks exactly like what you expect it to look like. So the one-tail test is way more specific. The two-tail test is way more general. And then you have to choose your test statistic, and that's going to be based upon your sampling distribution. So are you going to use a Z-test or are you going to use a T-test? That's going to be based upon the sample that you use, as we talked about in our last lecture. And then we move on to the next steps. So your next step is that you have to determine the critical value, and you get that critical value out of the chart that's in the back of your textbook. So you figure out what that critical value is depending on whether or not you use a one-tail test or a two-tail test. Then you calculate your sample statistics or your estimate for the population parameter. You calculate that based upon what's in your textbook. And then you calculate your observed value of the test statistics. So what comes out of your data when you actually use that formula. And then you have to compare those two values. Remember the critical value versus the observed value. Which one is higher? And the one that is higher determines whether or not you accept or reject your null hypothesis that there is no relationship between those two variables. So when do you reject the null hypothesis? In a two-tailed test, you're going to reject the null hypothesis when the absolute value of the observed test statistic is greater than or equal to the critical value. So if what you calculate is greater than or equal to what you find in the back of your textbook in that table, then you reject the null hypothesis. But if you decide to use a one-tailed test, then you have to take an extra step. The first thing that you have to do is to make sure that the estimate that you have is consistent with the alternative or the research hypothesis. So that's because you're using direction now. So directionality matters. So you have to make sure that what you see with that statistic is it goes in the same direction. So if that statistic that you calculate is like really high between the two groups, and based upon your theory and your hypothesis is really low and is going in the other direction, then you're not going to be able to reject the null hypothesis because it's not going in the right direction. But if it's going in the right direction and you make sure of that, then you're able to reject the null hypothesis if that value is greater than or equal to the critical value there. So you go to the same method as the two-tailed test once you reach that point. So here's our example that we use within our class, and we'll go through it really quickly so we can talk about that. So we're going to start off, we've read our literature and we came to the conclusion that, there should be a relationship between education and income. As education increases, education should have a positive impact on income. Education increases, income increases. So our null hypothesis would say that there is no difference between those who are highly educated, their income, and those who have lower levels of education. That would be the null. That's going to be the thing that we test from. We're going to test from the null. We do not test from the alternative hypothesis. So we start from there, and I have a 0 there because it's saying that there's no difference between those with low education and those with high education in regards to income. But the alternative or the research hypothesis would say that there is a difference. They're not completely equal. There is no 0 baseline between those. As education increases, then so does income increase. And then we have to make sure that we have to set our alpha level. And our alpha level refers to our level of confidence. So you remember those numbers we had before, 0.5, 0.05, 0.01, 0.10, 0.001. So for this example, let's set our alpha at 0.05 since that's the standard in political science. Now we have to decide what type of test do we want to use. Do we want to use a one-tailed test or a two-tailed test? Well, I want to get as much information as possible, so I'm going to use a two-tailed test, because what if the relationship looks inverse to what I think it is based upon the literature? What if I find something different? I still want to have a room to interpret that and to talk about that. So I'm making a decision that I'm going to use a two-tailed test. And now I have to decide what sort of test I'm going to be using for my study. So specifically for this, I'm going to use a larger statistical test called a regression analysis, specifically ordinary least squares regression. But within that test, there's something included called a t-test. We talked about those earlier. So the test that I'm going to use to determine whether or not there's a difference is a t-test, because I'm going to use a t-statistic. And with the t-statistic and a two-tailed test set at the 0.05 level, the critical value is 1.96. This is an important number for you to remember because it's consistently the critical value. These critical values don't change. It's the most common one you see. So the critical value is 1.96. When I go through, I'm going to go through and I'm going to run my analysis. I'm going to do my calculations. I did my calculations and my observed t-value comes out to be 2.278. So remember, the critical value is the number that you have to hit in order for there to be a statistically significant difference that exists within your data. In order for there to be a relationship there, you have to hit 1.96. So instead of doing 1.96, I did over 1.96. It's 2.278. And this means that my observed value is higher than my critical value. And since my observed value is higher than my critical value, that means that I have to reject the null hypothesis. So that means that I am 95% sure, pulling from my alpha level, that there is a statistically significant relationship between education and income. And that's the conclusion that I would draw there. So in general, what we were doing there is testing to see if there's a relationship between those two variables, but there are other tests that we can also conduct within research. And one is a difference of means test. And we use this test when we're interested in looking at the difference between two groups. Now, the two groups that could exist could be your sample and the population, or it could be two samples that you have. And we're going to talk about those different things. So let's start with the basic rule. The basic rule or the basic logic is that we want to determine if there is a difference that exists between two means is great enough for us to consider that there is a substantive and statistically meaningful difference. So there's one thing to have a substantive difference, which means that we can see on paper that these numbers are not the exact same thing. But that doesn't mean that it reaches the level of statistical significance. You could have a number that you have calculated for the mean of two groups, let's say their mean value on a test, and the mean or the average for one group is an 80, and the mean or the average for the other group is an 85. We know that there is a substantive difference between those two because 80 and 85 are not the same, but we don't know if there is statistically significant difference between those two groups. And that is what we use the means test to determine whether or not it is statistically significant, even though we know that it is substantively significant. And to do that, we use Z formulas and we also use T formulas. And within those different formulas, they're outlined in detail in your book. We have to calculate the denominator and the numerator. And the denominator represents our standard errors of the mean. And in order to determine whether or not there is a statistically significant difference, just like our last example, we have to compare the observed to the critical value. And if the sample is much smaller, we, instead of using a Z formula to determine this, we would use a T formula. Typically, we use a T when the N, or the number of cases, is below 30. That's typically like a standard that we use. So let's talk about what this stuff looks like in a little bit more detail. One form of means test that we see is testing the hypothesis about the proportions, and that's kind of like testing along the lines of ratios and fractions. And we use the same formulas that we use for our other difference of means tests. So if we have a smaller sample where N is less than 30, then we're going to use a T test to determine that. But if we have a larger sample where N is greater than 30, then we will use our standard normal distribution and our Z. Because if you remember from our last lecture, we use the T because the distribution is not considered to be normal, it's considered to be a little bit more flat. So we have to use a test that takes more factors into consideration and more uncertainty into consideration, that incorporates the flatness of the curves and considers different things like the degrees of freedom to accommodate that level of uncertainty that we have there. So with doing different types of means testing, we have a couple of tests that we use. We have the related samples test and we have the independent samples test, and they are exactly what they sound like. The related samples test is when you are testing two groups, because remember, difference of means is looking at two groups. When you have two groups, and instead of being two completely different groups with completely different participants, they're just two different tests from the same group. So this is what you see when you have pre and post tests. If I gave you guys a diagnostics test at the beginning of the semester and then gave you the same diagnostics test at the end of the semester to see how much you know about research methods, then that will be a pre and a post test. And in order to test and see if there's a difference in the mean score for the class, like was this class actually successful? Did you all learn anything? Then I would have to use a related samples test to do that. So I would take the mean from the beginning of the semester before we talked about anything, we discussed anything, before I taught anything, and I would compare that to the same students, their post-test results at the end of the semester once we've gone through all of that. And then you have the independent samples test, which is different because the samples are not related. In the independent samples test, instead of having a sample that is two separate measures for the same group of people, you have two separate measures for two different groups of people. And one way you see this happening is along the lines of demographics. Let's say you want to divide your group up into men and women. So you want to see if there's a statistically significant difference between men and women. Or let's say you have like racial groups. You want to see if there's a statistically significant difference between whites and non-whites. And I use whites and non-whites because this test is for two samples. If you want to look at more than two groups, then you have to use a different test. But you let's say men or women, whites or non-whites, or party ID. Let's say you have Republicans versus Democrats, and you want to look at their mean scores and see if there's a statistically significant difference between those two groups. With the independent samples test, it's also important to know that those groups may be different sizes. So it takes all of that into consideration in the way that they structure the formula. And you can see a number of these formulas. They outline them in your text really well to show you how to calculate them by hand. Now, I'm not going over that in detail because for the purpose of this class, going into how to calculate these things, it isn't really necessary. But I want you to be able to know what these tests are and when you would use them, because it helps you understand how to interpret the statistics, as well as when you're reading papers, you're able to understand what exactly happened and what exactly they used to determine whether or not there was a relationship between two or more variables. So here is an example of testing a relationship with two samples, okay? So here we're looking at a difference of means test with the related samples. And we're looking at, let's say, two groups who watched a documentary. We look at how much knowledge they have about certain factual questions. So these are voters and national security. We give them a pre-test before they watch the documentary, and then we give them a test after they watch the documentary to see what they know or how their knowledge has changed. So here we have the same group, but we have two different measures for that group. That's why it is a repeated measures sample here. So now look at the little chart I have on the right. So we denote what the null hypothesis would be. Null hypothesis denoted with the little 0 as the subscript. And we're saying that if there is no relationship between two, then we expect the mean, which remember is the bar, y bar, for sample 1 and y bar for sample 2, we expect them to be the same, which means 0 difference between the two groups. And we go through and follow those steps we talked about in the beginning of the lecture, and we calculate our t observed, and we also look in our chart and find our t critical. And we see that our t observed is 3.49, and the number that we had to hit was 2.086. So does this mean that we accept the null hypothesis, or does it mean that we reject the null hypothesis based on our observed and our critical value? Well, if you remember what we talked about a few minutes ago, this means that we would have to reject the null hypothesis because the absolute value of our observed value when we calculated it is higher than that critical value. We hit that number and exceeded it, which means we have to reject the null hypothesis. And that was our example for repeated samples. So now let's talk about the independent samples test. So in this test, instead of looking at differences pre and post test, we're looking at two different groups, two separate groups. We have second-year college students and their knowledge versus first-year college students and their knowledge on national security. I have included on the right a picture of the equation that you use to calculate those confidence intervals for the statistics if you choose to use the confidence interval method. We're going to talk about that in detail on the next slide. So we're starting with these two groups. So now let's look at what we get in our calculations as far as the regular t statistic. So we start with our null hypothesis, which says there is no difference between the two groups. That is where we start. We're saying that there is no difference between the two groups. And our alternative hypothesis, this time we're going to take a directional turn with it. We're going to say that group 1 is going to be greater than group 2. That is our assertion, that group 1 will be greater than group 2. So we go through the process, we've studied the literature, we've written our hypothesis, and now we've tested it, and we get our values. So our observed value is negative 4.21. and our critical value is 2.086. Now, with these two values, do we accept the null hypothesis or do we reject the null hypothesis? Well, in this instance, you would have to accept the null hypothesis. Now, you may be saying, how? How is that even possible? 4.21 is higher than 2.086, right? Yes, it is. It's higher. But the first step here, because we gave a directional assertion in our alternative hypothesis, we said that group 1 is going to be higher than group 2. The first step that we have to do is to see whether or not our observed value aligns with our alternative hypothesis. And if we look at our observed value for our alternative hypothesis, we're seeing less than for group 1 instead of greater than. So we can't reject the null hypothesis because it's not what our alternative says. If what you see in your statistics doesn't match what your alternative says, you still have to accept the null hypothesis. That negative sign was the big key that indicated that it was going in the wrong direction, because that group is supposed to be the one that's higher instead of it being lower, because this time we took a one-tailed directional test. But all of this is well and good, and it has very important values in doing studies and research and all that good stuff. But we cannot forget about understanding and interpreting. We did a little bit of interpreting before when we looked at those values and determined whether or not to accept or reject. But we have to take our understanding a step further when it comes to data analysis and drawing conclusions. We understand that we either accept or reject something, but what does that actually mean? You have to come to the conclusion that this means that there is a relationship that exists between those variables. In some instances, you may take it a step further and say that as this thing increases, the other one decreases, and it means that that one variable has a major impact on another variable, and talk about the interpretation there. But there's also this consideration for statistical significance and substantive significance. We talked about it briefly in the beginning. You have to understand that just because something reaches statistical significance, that does not mean that it has substantive significance. And there's an important reason for that. We're using statistical software or formulas by hand to calculate certain things. And when it comes to math and numbers, this is something that is very discrete and very concrete. Certain things always happen when you compute numbers. That doesn't necessarily mean that in social science it has a real world value or impact. I'll give you some of the things that impact statistical significance to show you this. The first thing is that as those numbers, the values in our two groups, the values, they become more and more different, the difference between them increases. Let's say one value is 10 and the other value is 1, then you're more likely to reach statistical significance for that reason alone. But does it have a substantive meaning? That's something that you have to consider. Does this really mean something in the real world? Because those numbers will tell one story, but you have to be able to interpret what that actually means in the real world. Numbers themselves, just because they got bigger, is going to give you that checkbox that says, yep, based on the observed and the critical, there is a relationship. But what does that relationship mean? You have to make that determination. The next thing is with sample size. We talked about this in the last lecture, that sample sizes that are smaller tend to have higher degrees of uncertainty. Well, sample sizes that are larger tend to have higher degrees of certainty. And because they have higher degrees of certainty, this means that you're more likely to get statistical significance just by increasing your sample size. When you do a study and you study 35 cases, your chances of getting statistical significance is low. But when you do a study and you study 3,500 cases, the chances of reaching some level of statistical significance is really high. But you have to be able to interpret and understand whether or not that actually has substantive value for understanding your variables. And the final thing is the size of the standard deviation. And the standard deviation is how far each value on average is away from the mean value of the group that you're using. And as the standard deviation becomes smaller, let's say you have a smaller standard deviation for your group of numbers, then you're going to have a greater chance of reaching statistical significance for that fact alone. So that means that when you have numbers that are closer to each other as far as their value, they're closer to the mean, then you'll get statistical significance just because you're computing numbers that are close to each other in a statistical software package. So those are all things to consider, because at the end of the day, the thing that is most important is the substantive significance. Being able to check a box that it reaches a certain marker as far as statistics is concerned is very important, and it's a major criteria that we use to judge whether or not research is valid. But you have to realize there is a way to lie with statistics. There are ways that we are able to tell stories that aren't really that major or don't have that great of an impact, just because of these things surrounding sample size, the difference between the values, and the size of the standard deviation. All of those things help people to be able to lie with statistics in a number of cases. So all in all, the big takeaways I want you all to have from this section in the book, talking about hypothesis testing and normal distributions and using z-scores and t-scores and all that good stuff, are the following four things. The first thing, you need to remember that you use different tests for different circumstances, depending on whether or not you're trying to see whether or not there's a difference between what you have in your sample and the population, depending on whether or not you have pre and post tests, depending on whether or not you're using two groups that you need to understand whether or not there's a difference between those two. Though all those things determine which test that you will use. The next thing that you have to remember, and kind of why I found it very important to make sure that you guys worked out your null hypothesis in the very beginning, is that your answers always lie with the assertions you start out with early on. You can't reverse engineer research. Whatever you start out with as your hypothesis is going to be the foundation of everything that you do when you move forward with testing. The next thing that I want you to remember is that those tests you use, they calculate numbers, but software packages are not smart enough to interpret them. So it's up to you to interpret those numbers and to be able to tell the story that you get from the data, instead of just being able to report a group of numbers. You need to be able to explain what those group of numbers mean. And finally, you have to understand that while you have a group of numbers, you need to be able to explain the statistical significance, real world value for our understanding of your social phenomenon. And I say that because we study social science. We don't study petri dishes with drops of some sort of chemical in a container. So it's very important for us to be able to interpret what we see here, because it has to have a real world explanation that can be applicable to political science, that can be applicable to public administration. Being able to say that there is a 0.01 difference in voters who are consider themselves liberal versus voters who consider themselves conservative is all well and good. But what does that mean in the real world? That is what you have to be able to explain on the back end of your research. What does that mean in the real world? So those are your big takeaways there. I'm going to go ahead and stop there, and we'll pick up with chapter 13 and all of the great things that chapter covers.